Hi folks, Mr. Ackerman here. This video deals with kinematic equations for uniformly accelerated motion, and you should probably be happy that there's these things called kinematic equations. A lot of students often ask me, is there a single equation I can use to just solve this problem? Well, kinematic equations, when we're dealing with motion, might just be the equations that you're looking for. However, you have to be careful when you use them. They can't be applied in all situations. So the topics we're going to cover in this video, first of all, are what are these equations and how do you use them, and when should you use them, and of course, when should you not use them. So keep that in mind. They are a powerful tool. They simplify calculations, but they are dangerous if used incorrectly. All right, so here we go. First off, I've taken an image once again from our textbook Physics 12 by Nelson, and it's actually a cutout of a chart that they have that just summarizes many of the equations that we're going to be using. Just to go through them, you probably are familiar with most of these. Like this one, A equals VF minus VI over delta T. Final minus initial, so that's really what we call delta V over delta T. Well, hey, yeah, that's the formula that you learned in grade 11 for average acceleration. So that's actually not a new formula at all. And in fact, we can rearrange, well, not this, but we can rearrange this one if I multiply the delta t up onto the other side so that I have a delta t. And if I have v final minus v initial on this side, and if I then just bring the v initial onto that side, I'm going to have a delta t plus v initial equals v final. And if I just rearrange that, and if I use what you did in grade 11, I think instead of final you had v2 and instead of initial you had v1, then this formula starts to look like v2 equals v1 plus a delta t. That should look familiar to a lot of you, especially if you had me in grade 11. So, hey, nothing new there. Everyone recognizes this formula. It's the big one. Delta d equals v1 delta t, or v initial delta t, plus a half a delta t squared. Maybe you don't remember it. You don't know it by memory, but everyone recognizes it. It's the one with the half a t squared. That's how I remember it. Delta d equals v av delta t. Is this anything new? No. Once again, just rearrange, divide both sides by delta t, and what do you get there? Those will cancel, and you'll be left with v av equals delta d over delta t. We'll say, oh yeah, that's the definition of average velocity. That's actually nothing new. It's one of the first things you learn when you talk about motion and calculations. Delta d equals a half vi plus v final divided by a half of that times delta t. What is this one? Well, focus in on these two. Focus in on this. Let me just rewrite that. Delta d equals, I'm going to write it this way, v initial, or v1 if you prefer, plus v final, or v2 if you prefer. I'm going to bring the half in underneath here, and then I'm going to go like this and go delta t. So I haven't changed anything. I've just sort of written it a little bit differently. v1 plus v2 divided by 2. Add up two numbers and divide them by 2, you get the average, right? In other words, this is just v av delta t. Hey, wait a minute. This formula is that formula. There's nothing new here. There is one formula that maybe you didn't encounter in grade 11, and that's this one here, v final squared, or v2 squared, maybe you'd see it written that way, equals v initial squared, or v1 squared, plus 2a delta d. Now just be careful, your book omits the vector symbol here, but they really should include them, because as we're going to see in an example in a moment, these vector symbols remind you that you have to include direction. If you don't include direction here, you will sometimes end up with the wrong answer. So let's just make a note of that. Include direction, or else you could end up in trouble. Okay, so there's our kinematic equations. There aren't really any other ones that you're going to need in this course. Just a couple things. We were talking back here that these equations are for uniformly accelerated motion. Now, it is a little secret in this course, maybe it's not a secret to some of you, that the motion we deal with will involve uniform or steady acceleration. We will never give you questions with changing acceleration. So imagine yourself driving along in the car and you're at a traffic light that turns green and the driver accelerates steadily. You get that nice smooth acceleration. That's uniform acceleration. Maybe some other day you're in a car with a driver who's very nervous and keeps pressing a different amount on the gas and then hits the brake, trying not to hit anyone. That would not be a steady acceleration. That would actually be what we call jerkiness. In fact, physicists call the rate of change of acceleration the jerk. You can look that up on Google if you want. I'm not kidding. I didn't make that name up. But that's what they talk about. We're not going to deal with motion with changing acceleration, jerky motion. We're going to deal with motion that is uniformly accelerated. So you can use these equations for all of the questions that we're going to do. Okay? Now let's just see these in action, and by doing that we'll see how are they used, when do you use them, and then we'll do a final example where you can't use them. So here we go. Let's see when to use them. Once again, taken from Nelson, the textbook, Physics 12. This is sample problem 6. It's on page 26 if you're following along with me. And they work it out for you, so I don't really have to say too much here, but I do want to add in a little bit. I'm going to show you my technique for solving these. This might help you, especially if you've forgotten how to do these questions, or maybe you're a grade 11 student watching some of the grade 12 stuff and you want to pick up a few hints to work ahead. So a curling stone, all Canadians know about curling. If you don't know about curling, just look it up on YouTube so that you know what this sport is about. The rock slides along the ice, and of course, as any rock sliding along a level ice surface would experience, it would probably experience a bit of friction. It would slow down. So the picture which they drew, which is very nice, shows you the rock moving in what they call the positive direction, but because there's friction slowing it down, they show you an acceleration that is in the opposite direction. So even though this rock is moving west, which is signified by this symbol and arrow here, the acceleration which is opposite that, east, is causing the rock to slow down. They tell you here's the acceleration, a very small acceleration of just a few centimeters per second squared. That's what the rock experiences as it moves a relatively large 28 meters to the west. And they also tell you that it eventually comes to rest. So they ask you for A, the initial velocity, and B, the time of travel. So how do I go about these? Well, what I do is when I'm trying to solve a question involving kinematics, I write out what's given, I write out what's required, and then I look for some link or some equation that will allow me to relate what's given to what's required. So in this column of this chart that I'm making, I'm just going to write out what's given. What am I given? I'm given that the acceleration is 5.1. Now that's centimeters, and this is in meters, so I got to make a choice now. I got to convert one of these units to the other. 5.1 centimeters is 0.051 meters per second squared, and that's east. I also know that the displacement is 28 meters west. Now you can see right away, if you don't know your symbols, this is going to be hard to fill out. So make sure you review your symbols that you learned in grade 11. They also say that it comes to rest. Now it wasn't at rest in the beginning, otherwise it wouldn't have moved anywhere. It's at rest in the end. So that's a V final, or a V2 of 0. You don't have to write meters or centimeters per second. 0 is 0. It doesn't need any units. Okay? What is required here in part A? The initial velocity V1. And so now I go to my chart and I look for a formula that has all of these symbols in it and only these symbols. Otherwise I'll have too many unknowns. Now if you look back, you'll see that this is actually the formula to use. It's got V2, V1, A, and delta D. So I'm going to borrow that, go back here. V2 squared equals V1 squared plus 2. Acceleration vector hat matters. It reminds me to use direction. Delta D vector hat also matters. Remember we talked about that. You better use the direction in this particular formula. Otherwise you're going to run into trouble, and you're going to see why in a minute. Let's see how that works. So V2 squared, 0 squared, equals V1 squared, thing I'm looking for, plus 2, now A, 0.051 meters per second squared, and that's east, times delta D, which is 28 meters west. Now, let's stop for a second. You can't mix an east and a west in these equations. You have to use one or the other. Now, luckily, an east is the same as a negative west, so I can call that W as long as I put in a negative in there. I could also have made this an east if it was negative, and then that would have stayed east. Doesn't matter which one you do. Let's see what happens. So we end up with 0 equals V1 squared. Now I got to get my calculator. I'm not too prepared here. Let's see what you get when you do 2 times 0.051 times 28. And I get 2.856. So I'm going to write that in there. Where are we here? And that's actually negative. So negative 2.856. 2.856 what? Meters per second squared times meters. That gets you a couple of meters. So meters squared per second squared, if you're really paying attention here. Okay? And keep in mind the direction is west. However, is it west squared? What's going on here? An interesting thing about this newish equation is that it actually doesn't have vector symbols. It's actually asking for speed, believe it or not. When you square a velocity, you end up with speed. When you square a vector, rather. So that's a little bit of vector trivia for you if you haven't taken vector calculus, or rather calculus in vectors yet. But when you square a vector, it becomes a scalar. It becomes speed anyway, if it's the velocity vector. So believe it or not, in here, we don't even have to worry about this west here. So I'm just going to grab an eraser and say, enough of you, you're out of there. Okay. So there we go. Now, just to finish this off, notice how I have a negative here, and I got to get this onto the other side of the equation. On this side, it's going to be positive 2.856 meters squared per second squared, equaling V1 squared. If I had not had that negative in there, I would not have a positive on this side. And then when I take the square root in order to get V1, I would have been taking the square root of a negative number, which is not legal. Now, how did I get this negative in the first place? Remember, I got it from paying attention to my vector directions. Having an east and a west in there forced me to make a change, which brought in the negative. Without that negative, when I come across the equal sign, I don't end up positive, then I can't take a square root. That's why I said, over here, you better include direction, otherwise your math isn't going to work out. And while it might not have been a catastrophe here, I'm sure most of you could have worked your way around this, sometimes it will lead to a problem in your calculation. Anyway, the rest of this comes out to some number. What's it going to be? I don't know, square root of 2.856. Calculator says 1.7 meters per second. So there you go. That's the initial speed. All right, so that's pretty straightforward there. And then finally in part B, they ask you what is the time of travel. So now if I make my given, required, and link or equation column there, what'll I have? Now I know a lot of stuff. I still know the acceleration from up here, and the displacement, and the V2. I'm not going to write in the numbers now. I'm just going to pick up the pace because I know you're getting sick and tired of my voice here. I know all this stuff now because I solved for V1 back in this part. It's still the same problem. Now they want the time. What equation links all of these? Go back to your list of equations and you tell me. there's actually a whole bunch of equations, possibly even all of them. Well, the only one that doesn't have time is this. We've already used that one. But I bet you we have v1, we have v2, we have displacement. We could use this. We know the displacement, we know the acceleration, we know the initial velocity. We could use this. Of course, if you use this one, you're going to have to solve a quadratic, so I don't know if you're really interested in that. You can get away from a quadratic by using this. And even this, we know, remember, this one becomes this. We know v2, we know v1, we know a. We can solve for time. So, I don't know, let's use that one. Here we go. We can do v2 vector this time equals v1 vector plus a delta t. We know that, we know that, we know that. So solve for this. Just straight algebra, folks. I'm not going to do it for you. You can follow along in the book, or if you don't have the book, you can try it on your own. I'm pretty sure you'll be okay at this point. Just as a side note, the book's answer, and I haven't checked this, but I trust that they're accurate, comes to 33 seconds. Now, if you ever watched curling and you've seen them send the rock down the ice, it doesn't usually take 33 seconds for it to come to stop. In fact, what usually happens is the rock is still moving quite rapidly at the time that it strikes some other rock, and you never really see it come to rest except as it gets shoved off to the side and hits the boards, or the odd time the rock may have a perfect collision where it just completely comes to rest. But this question, I think they are assuming, or they're suggesting, that the rock just slides along a huge, really long surface of ice and comes to rest all by itself. 33 seconds would be a really long time, so try to visualize the problem to see what's going on there if you can. These are real problems involving real life, and if you can try to visualize them, all the better. Hop onto YouTube to watch a little bit of curling for a few seconds if you've never seen it before, because I'm sure some of you haven't, and it's actually a lot of physics in that sport. Okay, I digress. Back to the topic at hand. We've now covered how to use the equations, when to use them, finally, when not to use them. Well, since these equations are designed for use when you have steady uniform acceleration, then they obviously should not be used when you have non-uniform acceleration. So, do not use if the acceleration is not uniform. When would the acceleration not be uniform? The acceleration won't be uniform, obviously, if it's changing. To give you an example, suppose you're driving along in your car, and you're going along there, coasting at a steady rate, and all of a sudden you see a ball roll out onto the road, and chasing this ball is a child. So obviously we don't want to hit the child. We want to stay safe here. And so, like a good driver, you're not on your phone, you're not looking backwards or anything, you're driving along. You say, oh, I got to hit the brakes. And so your mind makes a very quick calculation. It senses danger up ahead, and you shift your foot from the gas pedal to the brake pedal. Well, believe it or not, there is something called reaction time, and this braking doesn't happen instantly. It actually takes a fraction of a second to occur if you're paying attention. If you're on your cell phone, it takes a lot longer. During the time that you are reacting, you haven't begun to slow down yet. You keep moving at a constant velocity, which means there is no deceleration or acceleration in the negative direction. You only begin braking once your brain senses that there's danger and tells your foot to go onto the brake, and the car's braking system actually begins to work. All this takes time. This is where there is deceleration, a form of acceleration, negative acceleration. So if this is constant velocity, and this is what we call, let's say, uniform acceleration, you have two different kinds of motion. You've got the green motion that I've circled here, and you've got the red motion. Well, guess what, folks? You cannot use a kinematic equation once to solve this whole problem. What you're going to need to do is use a kinematic equation for this part. Oops, I apologize there. I did a bad thing. I zoomed out, and now you can't see what's going on. Hold on. I had this problem in a previous video and didn't know how to get back. There we go. Now I know how to use this software. Okay, sorry about that. Getting back here, you have your constant velocity, so there's a kinematic equation that you're going to use in this section, kinematic equation number 1. Choose from any of the equations in here, create a chart of the given required information like we did in the previous question. Use that to solve for what's going on here while you're reacting, and then choose a different kinematic equation for this part. So once again, in this part, go back and make a chart like we did in the previous question of what's given, what's required. Go to your table here and choose a suitable equation, and then combine the two equations. There's probably going to be two unknowns. This sounds like an algebra question, and it is, and then you should be able to solve. If you're wondering what is a good question to try that helps you practice this, you can try question number 24 on page 27. This question relates exactly to this situation. You will not be able to use one kinematic equation for the whole thing. You're going to have to use two, one for each part of the motion. And now you know when not to use these equations. Well, I guess the title could be called, you can still use them, but be careful how you use them. You've got to do them twice. Okay, folks, that's it. We've now answered all of our questions. How do you use them? When do you use them? And when don't you use them? And how do you get around that? Thanks for watching, and I'll see you again next time. All right, bye now.